The stiffness method of analysis can also be applied to determine displacements, support reactions, and member forces in trusses that undergo temperature change. So in this problem, we'll use the stiffness method to find member forces for a coplanar, that is 2D truss, subjected to concentrated forces and temperature change. The key concepts we will use are calculating fixed end forces due to temperature change, calculating displacements when there are fixed end forces, and calculating member forces when there are fixed end forces. And here's our truss. It is indeterminate with 3 members, 3 supported or constrained nodes, and 1 unconstrained node. We're going to determine the force in the members, all of the members of the truss, and all of the members undergo a temperature increase of 100 degrees Fahrenheit. The thermal coefficient for all members is provided, as well as the cross-sectional area and modulus of elasticity. The thermal coefficient and modulus are that of steel. And for this problem, the structure stiffness matrix, that is capital K, will be provided. And here's our approach. We'll begin by approximating the answer. Because we want something to compare to after our calculations in order to determine the reasonableness of our stiffness method results. When we start the stiffness method, we begin by partitioning the structure stiffness matrix. And we also need to calculate the fixed end forces. Due to the temperature change. Then we can find displacements. Then we can find member forces. And we'll wrap up by comparing with the approximation. Step 1. Let's approximate the answer. And to do that, we're going to perform approximate analysis, and so I'm going to consider each of these forces acting independently, and we'll superimpose the effects of the applied loads. Let's start with the lateral load. I'm going to begin by ignoring the temperature change. We'll deal with that afterwards. And I'm going to assume that the horizontal force that is the lateral force, is shared equally by the diagonal truss members. So let's draw a free body diagram of node 1 and apply our assumptions. We have just the 5 kip applied lateral load. We're not going to consider the 2 kip load right now. Force in member 1 due to just this load. Force in member 2. And the force in member 3. And the geometry of our structure is such that we have a 3, 4, 5 triangle to describe the slope of member 3. And this is 1 to 1, so we have square root of 2 for the hypotenuse describing the direction or slope of member 1. I'm going to label to the right rather is our x-axis, up is our y-axis. And now let's apply equilibrium. I'm going to start by summing forces in the x direction. And by our coordinate system, to the right will be positive. So we have a negative contribution for the horizontal part of the force in member 1, a positive contribution from the force in member 3, and the applied load of 5 kips. But our assumption here is that the force, the horizontal component of force in member 1 is equal to the horizontal component of the force in member 3. And so 2 horizontal components plus the 5 kips has to equal 0. So that horizontal component is a minus 2.5 kips. And therefore, the horizontal component of force in member 1, Fx, will be a minus F1x is plus this negative and this negative cancel, 2.5 kips. F3x, Fx is F3x, and that is therefore a negative 2.5 kips. And so let's convert that, or convert those, to member forces. The force in member 1 will be square root of 2 over 1 times the horizontal component. So we have the square root of 2 over 1 times 2.5 kips. We put those together and we get a positive 3.54 kips, and that member's in tension. Now member 3. We have 5/3 times the horizontal component, which is 5/3 times the negative 2.5 kips, and therefore the force in member 3, due to just the lateral load with our assumptions, is a negative 4.17. That is compression. Now vertical equilibrium. Based on our coordinate system, up will be positive. And so we have 1 over square root of 2 times the force in member 1 plus the force in member 2 plus the contribution from member 3, which is 4/5. And if we substitute in the values we have, we get 1 over the square root of 2 times 3.54 kips plus the force in member 2 plus 4/5 times the negative 4.17 kips. If we solve that for the force in member 2, we get a positive 0.83 kips. And so that member becomes tension. Now approximate analysis, considering just the vertical load applied. Again, I'm going to ignore the temperature change. Until we're done with our superposition, and then we'll address that. So we have just the 2 kips downward load, and so I'm going to assume that roughly 1/3 goes into each of the members. However, if I assume exactly 1/3 goes into each of them, the horizontal components won't provide equilibrium anymore. So I'm going to stick to just this vertical member since it has no horizontal component, and I'm going to say that 1/3 of the applied vertical load goes into the vertical member. And then we'll be able to calculate the other 2. So I'll draw a free body diagram of node 1. We have our downward force of 2 kips, unknown force in member 1, unknown force in member 2, unknown force in member 3. Remember, these 3 forces are not the same as the ones we just calculated because these are due to just the 2 kips and not the 5 kips. I'll identify my x-axis being to the right, my y-axis being up. Our geometry is such that this is a 3, 4, 5 triangle, and this is a 1-to-1 slope, which gives us square root of 2 there. So let's apply equilibrium. I'll sum forces in the x direction first, and based on our coordinate system, to the right is positive. I have a negative contribution from the force in member 1. I have a positive contribution from the force in member 3. So I can express the force in member 3 as a positive 1.179 times the force in member 1. Now vertical equilibrium. Based on our coordinate system, up will be positive. I have contribution from the force in member 1 plus the force in member 2, which we are going to assume its value, plus the portion of the force in member 3, and minus the applied 2 kip load. So if I take the 2 kips, move it to the other side, we have 2 kips equals 1 over the square root of 2 times the force in member 1. The force in member 2 we said will be the 2 kips divided by 3, and then we have 4/5 times the force in member 3, but we'll substitute in our expression in terms of the force in member 1. So I can combine all of these, move this to the other side, solve for the force in member 1, and I get a positive 0.808 kips. Now if I take this quantity, plug it back into here, the force in member 3 is a 1.179 times the positive 0.808 kips, and the force in member 3 we get to be a 0.953 kips. Now we superimpose those results. And this is ignoring temperature change. We have the force in member 1 will equal approximately 3.54 kips plus 0.808 kips. Which gives us a 4.35 kips in tension. Force in member 2 will be approximately a positive 0.83 kips plus the assumed 2/3 of a kip. And that gives us a positive 1.50 kips. The force in member 3 will be approximately negative 4.17 kips plus a positive 0.953 kips. And that gives us a negative 3.22 kips. Now if we consider just a temperature increase and not the applied forces, temperature increase would cause each of these members to grow. Since this is the longest member, it will grow the most. This one will grow a lot. This one will grow the least. And so the restraining action of the lengths of the other members means that as this one tries to grow a lot, it will generate some compression. And this one we expect will experience some compression due to just the temperature change. So if we take those off and say just the temperature change, then this member, in order to keep this node in equilibrium, must go into tension. So when we consider both effects, these quantities give me a sense of the answer, but I would expect that with a temperature change, we're going to have this tension plus a little bit of compression, so we expect it to decrease when we get our stiffness results. And in this case, force in member 2 is in tension due to the applied forces, the applied loads. With the change of temperature, we expect more tension, so we expect this one to increase. And the force in member 3 we found in compression, and we expect more compression, so we expect it to increase as a negative quantity. Now, if it does not turn out that way, we'll have to evaluate whether the results are still reasonable, and if we can justify why it doesn't work out that way. It might be due to the assumptions we made here, but these give us a good ballpark for the magnitudes, and these give us a good sense of which way those results should modify. Now step 2. we'll begin the stiffness method. And since we have the structure stiffness matrix, we'll begin by partitioning it. Because in order to find the displacements, we have to solve the following equation. The forces that are known at degrees of freedom, which will be the unsupported degrees of freedom. It'll be the applied loads, the 5 kip and the 2 kip, equals a section of the stiffness matrix that we'll call 1, 1, and it refers to forces generated at the degrees of freedom that are unconstrained due to displacements of degrees of freedom that are unconstrained. We'll multiply that by the unknown displacements, which are the unconstrained displacements, K1, 2, which refers to the portion of the stiffness matrix, which is the degrees of freedom, or the forces generated at degrees of freedom that are unconstrained due to displacements at degrees of freedom that are constrained. And so we multiply that by the known displacements, which are the displacements at the supports, and in this case those are all 0. There are no support settlements, and so this chunk of the matrix will be multiplied by 0, and this component then equals 0. We add to this known forces at the nodes that are fixed end forces. In this case, the forces due to the change in temperature. And so the only portion of the structure stiffness matrix we'll need is K11, the degrees of freedom that are unconstrained. And the degrees of freedom are numbered 1, 2, 3, 4, 5, 6, 7, 8, and down the rows 1, 2, 3, 4, 5, 6, 7, 8. Notice that all of these coefficients are multiplied by A and E. As we look at our structure, the only unsupported degrees of freedom are 1 and 2. So we'll partition our matrix by dividing between columns 2 and 3 and between rows 2 and 3. And so the section we need is this top left chunk, that is K11. If we had needed it, this top right chunk was K12. Now step 3. We need the fixed end forces. These are the forces that would be created if the nodes were locked in place and the temperature change occurred. And to calculate those fixed end forces for a truss element, we'll use equation 14-25. So for member 1, the length (8 feet wide, 8 feet tall). So we take the 8 feet squared, add 8 feet squared, take the square root. It's 11.31 feet long. We need the directional cosine. Lambda x is the change in x coordinate, and with this being the near node and this the far node, we have a negative 8 feet over the 11.31 feet, and our directional cosine is a negative 0.707. Lambda y is a positive 8 feet over 11.31 feet, and so that's a positive 0.707. And so our fixed end forces, near node x direction, near node y direction, far node x direction, far node y direction. We'll use the subscript naught to refer to it being fixed end forces, equals AE times alpha, which we said is 6.5, times 10 to the minus 7 per degrees Fahrenheit. We're looking at an increase, therefore a positive change of 100 degrees Fahrenheit. We need our directional cosines, lambda x minus 0.707, lambda y 0.707, minus lambda x, which gives us a positive 0.707, and minus lambda y, which gives us a minus 0.707. And if we put those together, multiply these two together, and then times the negative 0.707, I'll incorporate the AE inside the brackets. We get a negative 4.60 times 10 to the negative fifth times AE. Alpha delta t times the lambda will be the same, but with opposite sign. And we have the same here. And back to negative here. And so those are our fixed end forces, and they act at degrees of freedom. Near node in the x, which is degree of freedom 1. Near node, we'll label those, in the y, which is degree of freedom 2. Far node in the x, degree of freedom 3. And far node in the y, degree of freedom 4. Now member 2. Its length is 8 feet. Lambda x, well, there is no change in x coordinate, so that is 0. Lambda y, there is a positive change of 8 feet divided by the length, and so lambda is a positive 1 because we're going from this near node to this far node. So now our fixed end forces, near node in the y direction, far node in the x, far node in the y. AE times alpha times change in temperature times the directional cosines. Lambda x 0, lambda y 1, minus lambda x 0, and minus lambda y a minus 1. Put those together, multiply these times the directional cosine we get 0, 6.5 times 10 to the minus 5 AE, 0, and minus 6.5 times 10 to the minus 5 AE. And the degrees of freedom are near node X, degree of freedom 1, near node Y, degree of freedom 2, far node X, degree of freedom 5, and far node Y, degree of freedom 6. And now member 3. We have the near node at 1, and the far node is node 4. Our length will be the square root of 6 feet squared, it's a change in x coordinate, and 8 feet squared, change in y coordinate. Put those together, it is 10 feet long. Lambda x will be the change in x coordinate, that's a positive 6 feet divided by the length, positive 0.6. Lambda y is a change in y coordinate, which is positive 8 feet divided by the length, so we have a positive 0.8. And so our fixed end forces near x, near y, far x, far y, will be calculated by AE alpha which is the thermal coefficient per degrees Fahrenheit times the change in temperature times the directional cosines. We have lambda x, lambda y, minus lambda x, minus lambda y. We multiply these together times the lambda x. We get 3.90, 10 to the minus 5 AE. These two times lambda y, 5.20 times 10 to the minus 5 AE. And then we repeat the process with the negative signs, minus 3.90 times 10 to the minus 5 AE, and minus 5.20 times 10 to the minus 5 AE. And these are for degrees of freedom. Near node x is 1, near node y is 2, far node x is 7, far node y 8. Now let's combine all the fixed end forces for the structure. So we're talking about Q naught for the entire structure. For degree of freedom 1, we had this contribution from member 1 plus this contribution from member 2 plus this contribution from member 3. So we have the minus 4.6 times 10 to the minus 5 AE plus 0 plus 3.90 times 10 to the minus 5 AE. Degree of freedom 2. We have this component from member 1, this component from member 2, and this component from member 3. And so we have 4.60 10 to the minus fifth AE plus 6.50 times 10 to the minus fifth AE plus 5.20 times 10 to the minus fifth times AE. Then degree of freedom 3. Only member 1 connects to degrees of freedom 3 and 4, so only 3 and 4 will contribute fixed end forces to the entire structure. So we have 4.6 10 to the minus fifth AE and negative 4.6 10 to the minus fifth AE. Now degrees of freedom 5 and 6. Only member 2 connects to node 3, where degrees of freedom 5 and 6 are. So only the fixed end forces from member 2 contribute to the structure fixed end forces at degrees of freedom 5 and 6. So we have a 0 and a minus 6.5 times 10 to the minus fifth AE. And our last two, 7 and 8. Only member 3 connects to node 4 with degrees of freedom 7 and 8. And so the structure fixed end forces at degrees of freedom 7 and 8 come only from member 3. And so we have negative 3.90 10 to the minus fifth AE and negative 5.20 10 to the minus fifth AE. And if we evaluate these summations, for our first degree of freedom, we get a negative 7.0 10 to the minus sixth, and it's smaller because we have subtractive cancellation. These are all positive, and we get 1.63 10 to the minus 4, and then the others carry across. Minus 5, minus 4.6 times 10 to the minus 5, 0, minus 6.5, 10 to the minus 5, minus 3.9, 10 to the minus 5, and minus 5.2, 10 to the minus 5. All of these times A, which is 1 inch squared for this problem, and E, which is the modulus elasticity for steel in this case, 29,000 KSI. If we incorporate those, our fixed end forces become, we have the negative 7 10 to the minus 6 times the 1 inch squared times the 29,000 KSI, we get a negative 0.203 kips. Put these together, we get a positive 4.727 kips. These, we get 1.334 kips. These, a negative 1.334 kips. 0. These come together to give a negative 1.885 kips. These come together for a negative 1.131 kips. And the last ones come together for a negative 1.508 kips. And these are for degrees of freedom 1, 2, 3, 4, 5, 6, 7, and 8. Now we're ready to find displacements, which is step 4. And we saw previously that the equation we need to solve is this one. There are only 2 unsupported degrees of freedom, so this is a system of 2 equations and 2 unknowns. And so let's actually write those equations out longhand. For degree of freedom 1, the applied load is a positive 5 kips. So we have 5 kips equals the coefficient associated with force created in degree of freedom 1 due to deformation at degree of freedom 1. So this term times AE and A is 1 inch squared, and E 29,000 KSI. So the per inches squared cancels with inches squared, and we get it in units of kip per foot. Very good. That's all times the unknown displacement in degree of freedom 1, to which we add the coefficient that represents force generated at degree of freedom 1 due to displacement at degree of freedom 2, which is this term, times times A, 1 inch squared, times E, 29,000 KSI, times unknown displacement at degree of freedom 2. Then we add our fixed end force for degree of freedom 1, which we found to be a minus 0.203 kips. So if I take this term, move it to the other side, and combine it with the 5 kips, we get 5.203 kips equals, when I put this together, I get 2326 kips per foot times unknown displacement 1, and to which I add, we put these together, 110.4 kips per foot times unknown displacement 2. That's equation 1. Now our other equation. In this case, we're talking about the known force at degree of freedom 2, which is a minus 2 kips, and it equals our coefficient associated with force in degree of freedom 2 due to displacement at degree of freedom 1, 3.8058 times 10 to the minus third per foot. We'll put in A, 1 inch squared, E, 29,000 KSI, and all of that is times unknown displacement d1. Then our other coefficient, force generated in degree of freedom 2 due to deformation at degree of freedom 2, 2.332 times 10 to the minus 1 per feet times A times E times our unknown displacement d2, and to which we add our fixed end force, which we calculated to be this, 4.727 kips. If we take this, move it to the other side, and combine it, we get a minus 6.727 kips equals, we put these together, 110.4 kips per foot times unknown displacement d1, plus we put these together and obtain 6763 kips per foot times displacement d2. This is our second equation. So to solve these two equations with two unknowns, let's multiply equation 2 by the following quantity, a negative 110.4 divided by 6763. That's this coefficient divided by this coefficient, and then a negative sign, all times this equation. Then we'll add that new version of equation 2 to equation 1. And what will happen is the terms for d2 will drop out. So if I take equation 1, add to it this term times the left-hand side from equation 2, this quantity times this quantity, the minus signs cancel, and I add a 0.110 kips equals, and I have that term, 2326 kips per foot d1, and this term times this ratio means that I will subtract a 1.8 kips per foot times d1. So when I combine the left-hand side, I get a 5.313 kips. When I combine the right-hand side, I get a 2324 kips per foot d1, and I solve that. d1 is 2.286 times 10 to the minus 3 feet. Now I take this quantity and substitute it into equation 1. When we do that, we have a 5.203 kips equals 2326 kips per foot times 2.286 times 10 to the minus 3 feet plus 110.4 kips per foot times d2. When I combine these, move them to the other side, divide them all by the coefficient, I get d2 is a minus 1.035 10 to the minus 3 feet. So it moves to the left. No, this is the y degree of freedom. It moves down at node 1. This one means it moves to the right at node 1. With the displacements, I can now find the member forces. And that's step 5. And to do that, we'll use equation 14-30, which uses the displacements for the structure and the fixed end forces in local coordinates to obtain the far node member force, which is assumed tension. So if we get a positive quantity, the member is in tension. If we get a negative quantity, the member is in compression. So let's start with member 1. Its length we had previously calculated to be 11.31 feet with a lambda x of negative 0.707 and a lambda y of positive 0.707. So now we can calculate the fixed end force for member 1 in local coordinates, and that is given by a minus a e alpha times the change in temperature. And so for this member, that's a minus 1 inch squared, 29,000 ksi. Alpha is 6.5 times 10 to the minus 7th divided by F, or divided by degrees of freedom, and our change in temperature 100 degrees Fahrenheit. Put those together and we get a minus 1.885 kips. So the force in member 1 is A E over length times minus lambda x, which makes it a positive 0.707, minus lambda y, lambda x, which is a minus 0.707, and a lambda y, positive 0.707, times the displacements, and we need displacements for degrees of freedom 1, 2, 3, 4. And for 1 and 2, we found them here. But degrees of freedom 3 and 4 are constrained. They have 0 displacement. Then we add the fixed end force, which is this. So our first term is 2,564 kips per feet. We take this lambda times this displacement, plus this lambda times this displacement, That's this lambda times this displacement, which is 0, and this lambda times the last displacement, which is also 0. And then we add our negative 1.885 kips. If I evaluate this first expression, we have a 6.020 kips minus the 1.885 kips. And our final answer is 4.14 kips. It's positive. It is in tension. Now the force in member 2. The length is 8 feet. Lambda x is 0 because there is no change in x coordinate. And lambda y is a positive 1. Our fixed end force for this member, minus a e alpha delta t, is the same for member 1 because it's not dependent upon geometry, just material and section properties and change in temperature. So we still get a minus 1.885 kips. So the force in member 2 is A E over L times minus lambda x minus lambda y, positive lambda x and positive lambda y, times the displacements at degrees of freedom 1, 2, 5, and 6. And 1 and 2 we saw were 2.286, 10 to the minus third feet, minus 1.035 times 10 to the minus third feet. Degrees of freedom 5 and 6 are constrained, so their displacements are 0, and we have the fixed end force. So if I evaluate this expression in front, we get 36.25 kips per foot. We have this times this, 0, plus the minus 1 times the displacement, minus 1.035 times 10 to the minus third feet, plus a lambda of 0 times 0, plus lambda times displacement, but displacement is 0. If we put together this first term, we get a positive 3.752 kips minus the 1.885 kips, and combined we get a positive 1.87 kips. So member 2 is in tension. Now member 3. Its length we had calculated to be 10 feet. Lambda x we found to be a positive 0.6. Lambda y a positive 0.8. The fixed end force for this member, minus a e alpha delta t, will be identical to that for the other two members as well. And now the force in member 3. It's A E over L times minus lambda x minus lambda y, lambda x, lambda y. The displacements for degrees of freedom 1, 2, 7, and 8. 1 and 2 we saw and minus 0.035 times 10 to the minus third feet. Then degrees of freedom 7 and 8 are supported or constrained, therefore their displacements are 0, and we add our fixed end force. So we have 2,900 kip per feet times, so we have the minus lambda x times displacement 1 plus the minus lambda y times displacement at degree of freedom 2 plus lambda x times displacement at degree of freedom 7, that's a 0, plus lambda y times displacement at degree of freedom 8, that is also 0. And the fixed end force. I consolidate the first term here, I get a minus 1.576 kips minus the fixed end force, and combined those give minus 3.46 kips, which would be 3.46 kips in compression. Now we're ready for step 6. Let's compare our results with the approximation. So we're going to look at the internal force in member 1, 2, and 3. Let's look at our approximate result and our predicted change, because our approximate result did not include temperature effects, but our predicted change suggested which way this value would change when the temperature effects were added. And then let's look at our stiffness method results. So if we go back to our approximate analysis results, we had the three forces given by these three quantities. A positive 4.35 kips, which is tension. A positive 1.50 kips, which is tension. And a minus 3.22 kips, which is compression. Then our predicted change, we said that our prediction for member 1 would decrease, but for members 2 and 3, their magnitudes would increase. Member 2, more tension. Member 3, more compression. And then our stiffness method results. For member 1, we obtained 4.14 kips. That was positive in tension. For member 2, we obtained a positive 1.87 kips, also in tension. And for member 3, we obtained a negative 3.46 kips, that in compression. And if we compare these results now, the magnitudes are actually very similar. Our stiffness results match the predicted changes. Stiffness result here is slightly smaller than our approximate result. Stiffness result for force in member 2 is a slight increase over the approximate result, and the stiffness result for force in member 3 is slightly more compressive than our approximate result. So these results all check, and we can conclude that we have a reasonable prediction of the member forces for this truss subjected to these loads and a temperature increase. So now let's go back and review the process we took to get here. We began by approximating the answer so that we can have something to compare our stiffness method results to in order to evaluate the reasonableness of those results. In order to perform approximate analysis of this indeterminate truss, we decided to consider each of the two applied loads, the horizontal load and the vertical load, separately. So starting with the lateral load, we made our assumptions, which included ignoring the temperature change. We then found the force in each member. Then, while still ignoring the temperature change, we considered only the effect of the vertical load, and again performed an approximate analysis by assuming that 1/3 of the vertical load goes to member 2. We then calculated the force in each of the members. We then superimposed those results to find our approximate results, or our prediction of forces in each of the members. I didn't specifically perform approximate analysis due to the temperature change, but we looked at what types of forces, tension or compression, would be generated if only the temperature change occurred. And I then used that information to superimpose on top of our approximate results and to predict which way our approximate result should change when we consider or look at, compare with, the stiffness result. We then began the stiffness method approach. The structure stiffness matrix was already provided. We just partitioned it and pulled out the piece we needed, and then began calculating the fixed end forces in global coordinates. We began with member 1, then member 2, and finally member 3. We then combined those results to get the fixed end forces for the entire structure, all 8 degrees of freedom. We were then ready to combine the stiffness matrix coefficients with the fixed end forces in the equation shown here. And since there were only 2 unsupported or unconstrained degrees of freedom, our system of equations is only a 2 by 2, 2 equations, 2 unknowns. And so we plugged in and found equations 1 and 2, and then solved them simultaneously for displacements 1 and 2. I then used those displacements to find the member forces, and we began with member 1, remembering that there are fixed end forces at the end of the member in local coordinates as well. We then found that member force for member 2, and then member 3. We wrapped up by comparing those stiffness results with the approximate analysis results and the magnitudes match fairly well. When we superimpose the predicted change because of the temperature change for members in the truss, then our stiffness results look reasonable, and so we conclude that we have an accurate prediction of the forces in each of the members. Well done.